So this will be the review for Chapter 7. So the first section of Chapter 7 was integration by parts. So you'll remember that this works, so the formula for integration by parts is this really funny formula. It's the integral u dv is uv minus the integral v du. And so what this means, the whole point of this thing is it allows us to, so this is a formula. This is an integration technique. It's an integration technique that allows us to change what we're integrating. And what it allows us to do is it allows us to, take the derivative of one thing, integrate another thing, and hopefully, by doing that, it simplifies the integral. So hopefully you've done some of these by now and you know what I'm talking about when I'm talking about it by integration by parts. But the big point of this is I get to pick u and I get to pick dv. But the idea behind this is, whatever I pick for u and dv, it all has to come together to be that entire integrand. Once I pick u, I calculate du, and once I pick v, I integrate it and calculate v. So whatever I pick for dv, I have to be able to integrate is the big thing there. And so there are some cases. There are a few problems where this is really useful. One example of a problem where it's really useful is if you had something like x to the fifth, e to the x. And you look at this, and if you've been doing these integration by parts problems, you know that this is going to be a really disgusting problem. I think I've had to do this problem at one point in my life. It was for a physics class, though. And you get good at doing integration by parts if you do it enough. I can sometimes, if the functions are simple enough, I can do a couple rounds of it in my head. But this is kind of crazy. But the point is, if I differentiate this 6 times, that x to the fifth will go away. And because I'm going to have to differentiate this 6 times, I can integrate this 6 times. And, I can integrate e to the x very easily. Integral of e to the x is e to the x. So the point behind this is, integration by parts works for this one because I can take the derivative of x to the fifth, and eventually it'll go away. And I can integrate e to the x. So this is an example where I can make a term disappear after so many derivatives. And this is kind of the archetypical example. This is what I'm usually looking for when I do an integration by parts problem. That's how I know something's an integration by parts problem. The next example we had was something like e to the x sine of x. This was an integration by parts problem. But the idea behind this one was, I integrate by parts twice. So I integrate by parts IBP. I integrate by parts twice. And it gives me an equation to solve for the integral. You can check out my videos for this one. I do something similar to this one. Can't remember if it's e to the x sine of x or e to the x cosine of x. I do one of them though. The point behind this one is, I can see that I can integrate this, and I always get the same thing. And if I differentiate this twice, I'm going to get sine of x back. And that's how I know that, this is something I'm going to be able to eventually solve an equation for an integral. Because eventually I'll return back to the same expression I had before. The other example, this was a homework problem, was something like ln of x squared over x to the fourth or something similar like that. This is an integration by parts problem. So the point behind this one is if I differentiate ln of x squared twice, it's no longer, I no longer have a natural log. So if I differentiate that twice, it becomes something in terms of, 1 over x is 1 over x squareds. I don't mean actually differentiating it twice. I mean, integrating by parts twice. That's probably a better choice of words for that. So, if I do it once, I'm going to get something like ln of x over x. And, if I do integration by parts on that, I can get rid of the ln of x. This was a homework problem. It's a good problem. I like that problem. Just because I hadn't run into that, in my stuff I do, research stuff. And so those were pretty much the three main types of problems that we saw here. The last thing I'll make a note of is definite integrals. So if you have a definite integral, a to b, u dv, so integration by parts, the way you do this is you do the integration by parts, evaluate this, and then the integral here you use stick bounds on. And that's how you do, so I did some examples of that also where we had a definite integral. Section 7.2 was trigonometric integrals. So there's a chart in your book that you're welcome to look at. I'm not going to write it down because it's going to be too much. These are, integrals of the form cosine squared, sine cubed, cosine squared, sine squared, cosine squared, tan cubed, secant squared, things like that, all these different problems you can think of. And there are certain rules, but I don't really, you can go and, look at that chart. I don't ever really do that. What you're looking for is you're looking to use the identity sine squared of x plus cosine squared of x is equal to 1. Or, you can get this, you can, divide this identity by cosine squared, and you're going to get tan squared plus 1 is equal to secant squared. So one of these identities you're going to be able to use in order to get your integral in terms of, a bunch of powers of sine and cosine, and then one power of cosine or sine, and you're going to do a u substitution. So you're going to use this and make a u substitution. I'm not going to go much further into that. There's a chart that tells you what you're looking for the different values of m and n with the powers. There are I did a ton of examples with this section. So if you need to go look at that, go do that. Section 7.3, we had trig subs. So the idea behind trigonometric substitutions is if I have integrals of the form x squared minus a squared, square root a squared minus x squared, square root of a squared plus x squared. The list goes on and on. But you could have also 1 over the square root of x squared minus a squared, x squared over square root of x squared plus a squared, whatever you want here. It's going to be, some square root usually. So usually just some sort of square root here, and you're not able to make a u substitution on this. But, the big ideas were, if I have x squared plus a squared, your substitution was x is equal to a tan theta. This is because tan squared plus 1 is secant squared. And you're looking to capitalize on that fact. X squared minus a squared, you're going to do a is equal to secant theta. Again, this is because secant squared theta minus 1 is equal to tan squared theta. And if you had something of the form a squared minus x squared, this one is going to be x is equal to a sine theta. And this is because cosine squared is 1 minus sine squared. And so, based on the problem, what you're really trying to identify is, which of these cases do I fall into? Do I have an x squared plus an a squared somewhere, x squared minus an a squared minus x squared? And it doesn't always have to be a square root. Somebody sent me a problem earlier it was like 1 over 1 plus x squared all squared. You can use a trig substitution with that also. That works. That might actually be the only way to go around it. I didn't try and do it any other way. Once you make the trig substitution, you calculate dx and plug it in. The last thing you have to set up that triangle where this angle here is typically like the arctan of something, or the arc sine. Something like that. And then you're what you'll always end up doing with these problems, if you're doing the indefinite integral, is you'll always end up trying to calculate something like sine of the arctan of x over 2. And so what you do is you set this up and you say, okay, this angle here is arctan of x over 2, and tangent is opposite over adjacent. So the tan of arctan of x over 2 should be x over 2. So in order for that to happen, this has to be the opposite side. 2 has to be the adjacent side in order to have that ratio hold. And then you figure out what the hypotenuse is. In this case, it's x squared plus 4. And then you can use this triangle to figure out what the sine of that angle is. Sine will be opposite over hypotenuse. And then you can just write that. So you'll write your answer in terms of, instead of these these arc functions, these inverse trig functions, you're going to write it in terms of all x's. So that was the idea behind trig substitution. Again, I've done plenty of examples in in my notes. So you're welcome to check there. Section 7.4 is partial fractions. So what you need to remember for this one is if you have, a fraction like this, the partial fractions for, these linear factors are all going to be the same. Sorry, this is supposed to be a capital C up there. And so the idea is, I can split, if I have something that looks like this and I'm trying to integrate this left-hand side, I can make it a lot easier because, if I have this integral, I can split this up into 3 integrals then. And each of these integrals are really easy to do. They're just logarithms. But, I have to set up my system of equations to solve for A, B, and C first. So you've done that before. For example, 1 over x minus 1, x plus 1. This is going to be a over x minus 1 plus b over x plus 1. The idea is, we want to put these over a common denominator. And the common denominator is always whatever the denominator of the left-hand side is. So in this case, you're going to put this over x minus 1, x plus 1. And in order to get the x plus 1 on this first factor, you're going to multiply the top and bottom by x plus 1, so you're going to get a times x plus 1. Same thing for b. You're just going to multiply by x minus 1. You may need to do some polynomial long division first along the way. I'm not going to get into that because, again, that's an algebra thing. You should have seen it before. You should have had some practice by now. If you're still shaky with it, you're welcome to reach out to me. We can go through some problems. And then from here, you can set up a system of equations, ax plus 1 plus b x minus 1. And when you want to separate these into powers of x. So this is going to be a plus b and then plus a minus b. And so the idea is, these are two polynomials. When are two polynomials equal? When the coefficients of all their variables are equal. So, you have a 0 on here for the x. So you have a 0 on the left-hand side for the coefficient of x. So the left-hand side, you have 0 in front of x. On the right-hand side, you have a plus b in front of x. On the left-hand side, your constant term is 1. On the right-hand side, your constant term is a minus b. This gives you a system of equations to solve for a and b. You can solve those, and then that allows you to split up the fraction into this, and then that allows you to integrate. And then, so the next question was, okay, what if I have something that looks like 1 over x plus 1 squared? What does my partial fractions decomposition look like for that? Well, the idea, and I walked over, I went through an example of why this is. The partial fractions is, so let's not do squared. Yeah, let's do squared for the first one. But so it's going to be a over x plus 1 plus b over x plus 1 squared. And the idea is, if I, let's make that x. Yeah. So just so it's not, because that system of equations is really easy to solve. But the big point is, whenever I have, something that breaks up into a linear factor with a power, I have to include all powers up to that power on the left-hand side. So if I had something like x over x plus 1 to the 30, I would do a over x plus 1 plus b over x plus 1 squared plus, I would keep going, and eventually I'd run out of letters of the alphabet, so maybe go over to the Greek alphabet. So x plus 1 to the 29 plus beta over, sorry, it's supposed to be 29, beta over x plus 1 to the 30. And that's going to be my partial fractions for something that looks like that. The last one we had is, what if something doesn't factor? So what if I have, x over x x squared plus 2. So this term does not factor. So this term doesn't factor. So its roots are complex. So its roots are plus or minus square root of 2i. Plus or minus I radical 2, better way of saying that. So the way we deal with this one is the factors for this one, you're going to be able to have, a linear factor up top, and then on bottom, you're going to get something that looks like this. And this isn't a problem that you would try and do this for. So maybe if I, added an x plus 1 there, that would be a better problem. And then you would get c over x plus 1 here. That's a better problem. And so what you would do is, you would again solve this system of equations. It's all just knowing about what kind of factors lead to the different partial fractions decompositions. And then, again, this one can be integrated. It can be integrated by u substitution, and this one is a logarithm when you integrate it. And so that is pretty much the exam. Section 7.5 is just integration strategies. They're really, the only way to test that is, just to hand you an integral and say, do this integral. And you're going to have to, in real life, that's how it is. If you're handed a problem, it's not, do this to solve the problem. It's, figure out how to do this problem. So I'm not going to cover any of that. You're welcome to read through it. There's any of the problems from that section are going to be problems from, these sections that I've gone over. So I'm going to stop here. So if you have questions or I wasn't clear about something, you can send me an email, leave a comment on the video. But